Hello, this is Paul from Foresight Tech. In this lecture, we're going to define what is a definite integral using limit definition, and then going to evaluate. The first, we have a notation. Here is the notation for what is definite integral, and this definite integral used to describe the area on the curve, as we described in the previous lecture. And in this notation, f is the integral function, a and b is the limit or the interval to integrate, and the dx is the increment, okay, or delta x, we simply say. First, I summarize something here, and which are the most important for us to evaluate using limit definition. We have a basic foundation, which is the theory. See, if f, the function is integrable on a to b in the interval, and then what is the area integrable? We just see the last term, right? If we're going to find the limits always exist for Riemann sum. Okay, so the area we defined it as this, the limit of the Riemann sum. Of course, everyone remember the index I is from 1 to n, which means right endpoints definition, approximation, right? Okay, so we know how to find the delta x increment, and how to find the dividing points. X0 is a, and xi is a move right I times delta x. Okay, so this theorem tells us we can use the definition of limit to find what is the area, and the area we define as the definite integral. Okay, this is the major purpose of Calculus 2. So how to find this? We need to use some rules. Okay, some results. The first result we call the sums of powers. So we have the first, this is the power 1, this is the power 2, and this is the power 3. Okay, and all these results can be proved by mathematical induction. What does this mean? The first I put here, so you can see this is summation, right? So I from 1 to n add together, I from 1 to n add all together, means the summation equal this. Okay, this is very famous. The second, this is power 1, right? 1 raised to the power 1, 2 raised to the power 1, n raised to the power 1. The second is power 2. Okay, we have a results. The third one is power 3. The more, okay, so we have power 4, power 5. If you go to Google, you can find all the results. Very beautiful, very useful for you. Okay. So another rules is summation rules. We remember this sigma is summation, right? The sigma notation is summation. We have these 1, 2, 3 rules. The first, if here c is just a number, constant number, does not matter, is not related to I, not dependent on I, and this means what? Each term is c, so c plus c plus c, how many n terms added together, so it's just n times c, right? This is easy. So the second summation is this, sigma is summation, each term is c, constant number times ai. I is dependent on this, ai is dependent on I, right? But the c does not depend on I, so c can be factored out, right? So we simply say it is we say c can be factored out, okay, up here, and this means factored out. Usually we say it's just factored out, right? Why? Each term c times a1 plus c times a2, and then factored out. If I wrote a little bit here, like ca1 plus ca2 plus goes on, plus c times an. This is the left, right? So how to get this? Factor c out. What we have is c times parentheses a1 plus a2 plus, oh, Okay, I mean, if you see constant number, you can factor it out. This is one rule. We have another rule. So AI plus BI, take a sigma, we can separate, or either we do the difference, we can separate. And usually we call this is the sum or difference rule. Okay, difference rules. How do you prove this? So I will not write it down here, so easy to imagine. So the first term is A1 plus B1. The second is A2 plus B2. All the terms we can group, right? So easy say you can group, or we say is a compound like a term. Compound like terms. I mean, so you can put all A together is the sum of A. If you put all B together, it's the summation of B. Okay, means separate. This is the sums of power and the summation rules are very important for us to do calculation later. Now let's look at one example. Okay, so here are the questions. Use the definition, limit the definition of integrals, right endpoints, right, to evaluate the integral. Evaluate the integral here. Okay, so this integral function is there, right? The integral function, you know, this we call the integral function. Integral function. And this function is the easiest function, the power function, right? So power function, remember we have sums of powers can help us to get what is the limit. So let's move on to the questions. So how to use the definition? Remember the definition is here. So integral is the limit of Riemann sum. What we need to do is find the Riemann sum. Find the dividing points delta x and then plug into the Riemann sum, take limits. The limits we use the sums of power. We can. So the first we need to find out what is delta x, right? So I put it here. So delta x, we have this. Its definition is b minus a. Okay, so this is a, this is b, right? So I will not write. Then divided by m is 1 minus 0 divided by m, which is 1 over m. Okay, so this is good. Then we're going to find out what is dividing point xi. I go from 0 to n, right? So the definition is this, is x0, which means a, which means 0 here, plus I times delta x. So this is the definition, to evenly divide. And then we plug x0 is 0. I times delta x is 1 over m. And then we wrote in this notation, is I over m. Yeah, that's good. We have almost everything. Then plug into just the limit definition. Okay, so I wrote here. The original 0 to 1. You can see this is f, right? If I simply say give a name, I have to give a name. This integral function I said is fx. So now we can say, okay, here is f x dx. How to get this? So this should be, use the limit definition, is the limit m approaching infinity, and the Riemann sum is I index 1 to m. So here is f at x I times delta x. So this is the limit definition. So this is a limit definition. Of course, this definition we use a right endpoint, right? Right endpoint. You also can use the left endpoint or the middle endpoint or any other points, but it is the easiest one. Okay, and then we do calculation. What is this? This should be equals I plug xi here. I plug delta x first. Please be patient. This we need to do a longer calculation. You need to go through step by step. Okay, follow me. This is the limit m approaching infinity, and the sigma I from 1 to n f. I guess I is that I recommended, I suggest you to don't skip, okay, don't skip steps, because we have a lot of calculation. Don't skip, otherwise it's easy to make a mistake. Delta x is there, okay, so at times 1 over m, and then we look at this. Remember, so this is a number, right? Does not depends on I. Remember, we have a rule, summation rule. This we said it can factor out. We can factor this out, or we simply say this factor out. Okay, so we can factor out, right? 1 over n. This is a summation rule. Remember that. So one of the summation rule we just discussed. Okay, if you forget, is this. This is summation rule. Okay, it's this constant number does. What does constant number mean? Which means it does not depend on I, the index. So this constant number can factor out. Okay, factor out. And if we factor out, then it's good. And then what do we have? We have this limit m approach to infinity 1 out of n. So 1 out of n is depends on the limit n, right? Cannot take out to the outer side, you cannot, but you can do this. I is from 1 to n f I over m, right? Or you can simply say this is a factor out, put it to here. Okay, this is a factor out. Okay, in this way, so we're going to need to input this function, right? So we plug into the function where this function, this function is there, okay, the integral function. What is x? We just plug this x there, and then we find this notation a little bit longer now, equals limit m approach infinity 1 over n is still here, then sigma I from 1 to m. Okay, so this is the function. I plug in. Should we get this? X raised to the third power, which is I over m raised to the third power minus 3 times x squared. X is this I over m and then square. Okay, we just plug in, right? And then what do we need to do? So I'm going to cancel this small parenthesis because it's a little bit simple. So everyone look at this notation, and this is limits, very complicated limits, but don't worry, we have the sums of power to help us get the answer. Simplify first, m approach infinity 1 over m sigma I from 1 to m, and this term I raised to the third power, n raised to the third power, I wrote it in this way, third power times I raised to the third power minus 3 I squared and over n squared, which is 3 over n squared times I squared. Why we do this way? Put this first. Why we do this way? Because this is the power, okay? I squared, I to the cube, I raised to the square, I squared. This means the sums of power we are going to use, and this is the coefficient. This is we call the coefficient. Okay, coefficient. This is also coefficient, and this is the major one we need, because this one is depends on I, and this coefficient does not depend on I. Later we can factor out again. Okay, so going from here and going to the, we have to go to the next page. Look at be patient. I need to copy, so like I put here first, and then this equals like this. Okay, and this step first, this is summation. We have a rule, so the summation ai minus bi, do you remember? We have a difference rule. Okay, remember this? I'll put it here. So AI minus BI is the sigma AI minus. We use this difference rule, okay, to get this is the limit m pot g infinity 1 over n step here, and this time we have 2 sigma, right? So this one minus this one, we have 2 sigma. Put this, okay, I equals 1 to n. The first term is 1 over n third power times I raised to the third power minus the second term is this another one 3 over n square times I square. See, and one summation, 1 sigma goes to 2 sigma. This is what we use, summation rule. Remember this is the summation rule we used. Which rule? A difference rule, right? Difference rule we use here. And then, okay, we don't need it. I'll take this away. And then let's focus on these questions now. Okay, wait a little. I get it a little bit clear for you. Yes, good. Okay, almost be patient with me. Now how to do? Okay, so we can distribute it, right? So this is a number, this is the difference. We can distribute this, distribute that. Okay, so we can go into distribute. Distribute, we have m minus n pot to infinity. So the first term should be like this. Now I have to put a big parenthesis, 1 over m sigma I from 1 to m, right, times I third power minus 1 over n. See, distributed, right, times the second term I from 1 to m, 3n square times I square. Okay, so this is just a distribute, and this, you know, is easy. And in this way, so now we can do what? We can factor out again. Remember, the coefficient, right, does not depend on I. We have factored out the rule, our summation rule, so we can factor this out to there. The same for this coefficient, factored out. See, what do we have now? We will have this m pot infinity. So as the upper the big parenthesis. So this times this now is goes to 1 over n raised to the fourth power, and then we have a single sum of the power. Okay, what the power? This is the remember we have this, right? This is the sum of powers. So we just shoot you results, and then this is this time this is 3 over n raised to the third power times summation sigma I from 1 to n I square. That's very good. See, now we have, right, what did we use this? We use factor out. You simply say is a factor out here, and then now we know what is. This is the power, right? This is a sum of powers. This is sum of powers. We just shoot the results. Okay, this is also sum of powers. Okay, and remember we have sum of powers where? Okay, here, see the sum power this square, the sum of power this. We're going to plug these results into this expression, and then we will find out what we need. Now is what we plug in here m pot infinity. So the first is the I put, so this is complicated, so I put here, I use this. Okay, 1 over n raised to the fourth power. Remember what this results? This result is this. Okay, m plus 1 over 2 square. Okay, so let's going to look at. So this is the cube. The cube is this result. We plug in here, and then this is the square. The square is this result. The square is this result. Is times. Remember here is 6, right? So here is n plus 1, 2m plus 1. Okay, I put a big parenthesis. Okay, now what do we need to do? we're going to simplify this term, okay? And to simplify this term, how to simplify? I will do separate. So let's look at do this, okay? So this equals what? We're going to do here 1 over n the 4. Square go to the top, square to go to the bottom. Okay, so we have n square, right? n plus 1 square over 2 square, which is 4. And then we can cancel something. We can cancel the power 2, the power 2, we have 2. Now this equals what? No, this not. We totally cancel, right? So this is cancel, we get a 0, which means 1, totally cancel. So we have this 1 out of 4, n plus 1 square over n square. Of course, we can merge the square together, which is this n plus 1 over n square, right? And then is 1 over 4. So this we can change it to 1 plus 1 over n square. We need this term. Why? Because this term is easy to find the limit. So now I put here n approaching infinity. And the first term, I prolog this, which means 1 over 4, 1 plus 1 over n square. The same. How about this term? We're going to separate. This term is here. First, I cancel 3, and then I cancel what? I cancel n. What do we have is 1 over 2, right? Times. So the top we left n plus 1, 2n plus 1. The bottom we left n square. N square, I do this, put n here, and then here. Why? We just merge them together. So 1 over n, so this term is n plus 1 over m. This term is 2n plus n over m. And now we can write the easy way. Okay, this is 1 plus 1 over m. This is 2 plus 1 over m. Why? This is easy to find the limits, right? The limits is this is 1, the limits this is 2, because 1 over n equals to 0. And then we'll plug this answer to here, which is 1 over 2. 1 plus 1 over m, 2 plus 1 over m. Okay, and almost. So now the limits, we can see these limits goes to 1, right? These limits goes to 1. These limits goes to 2. Okay, now we have almost. So the limit is, the first is 1 over 4 times 1 minus 1 half times 1 times 2. Okay, and this is easy to calculations. 1/4 minus 1, which is a negative 3 over 4. Okay, don't worry, this is a negative. Probably you will say why the area goes to negative. Okay, because okay, we have this definition. Keep in mind, I draw a graph for you. Okay, like here. If this is a y equals f equals the function, so we're talking about the definite integral. Okay. See, if this is a, this is a b, and the middle term is c. So we look at it. The first, this is a positive area. What does positive integral? I mean what? The area is always positive. This means the integral from a to c, fx dx is greater than 0. Why is greater than 0? Remember, so when we're going to find the area, delta x greater than 0, the function, the height greater than 0, so everything is greater than 0, right? However, for here is less than 0. Why? The second, we say from c to b, fx dx, this way always less than 0. Go beyond the x-axis, this is less than 0, the definite integral. Why? Because we use the definition, remember? So the height goes to negative. fxi times delta x. Delta x is positive. F at xi, the height is negative. Okay, the value of the function is negative. So the Riemann sign is always negative. Take a limit still negative. See, and this is possible if the area, the absolute area here is bigger than the negative one is bigger than positive one. So we can get this. Is possible. Be sure it is possible. Okay, is possible. So this is the first example. Okay, thank you.